So this one does not have a log on both sides, so we can't ignore it, right? When there's a log on one side, we're going to change it to exponential form. So this we're going to change to 6 to the third equals 7k minus 1. Okay, 6 to the third is 216. Is that right? Do I have an answer key? Okay, adding 1, so that's 217 equals 7k. So k equals 217 over 7. Okay?
Thank you.
You're welcome. Good. More questions? You guys are going to ace the test? Yes, Allie.
Can you do number 2 on homework 8?
Number 2 on homework 8. Yep. Huh? There's a paper towel right there. Go ahead. Okay, so what's the problem with this one, Allie? What's making this different?
I don't know. I just
Didn't get the right answer?
Yeah.
Okay, so tell me what I should do. Well, if we look at it, right? The problem is that on this side I have 2 logs instead of 1. How can I make those 2 logs into 1 log? How can I condense this side of it? So we have log base 9, but then we have subtraction. What do we do when we have subtraction? Divide. So we have 108 divided by 4. Okay. Now that I have just the 1 log on each side, we're going to separate or drop the logs out of there. 8y minus 9 equals 108 divided by 4. Okay, so when we have logs on both sides, but it's more than 1 log, we have to use our properties of logarithms to get it into this form. We want it in the form of log equals log. Then we can just drop the logs out. Okay, so now I have 8y minus 9. Let's see, that's 5427. Okay, and we'll add 9. So 8y equals 36. So y equals 36 over 8, which is 18 over 4, which is 9 over 2. And there's our answer. Okay, does that make sense? Please make sure you study for this test. Okay, it's going to be challenging. But if you study, it won't be. Okay, more questions. Okay, give me a fist of 5. Tell me how you're feeling about the test. Wow. Okay. Good. Excellent. All right. Okay, everybody stand up. Stand up. Whoop. Whoop. Okay. We're going to do some morning calisthenics. All right. Shake your hands out. Shake them out. Okay. Flap them like this. Right? Get the hips moving. Get it moving. Let's go. Get it moving. I want to see you all moving. Let's go. Get it moving. Get it moving. Okay, while your hips are moving, start turning around. Right, turn around. Turn around. Woo! Gotta go the other way. A little dizzy. Turn the other way. Okay, hands on your hips. Right, spread your legs. Bend over. Stand up. Bend over. Up. Come on, Alex. Over. Up. Come on, Alex. Over. Up. Come on, Alex. Over. Up. Alex, I'm getting tired. Over. Okay, ready? Jog in place. Baby steps. Baby steps. Okay, baby steps while you're turning around. Okay, everybody kind of just move around, run around, make it ass. Yeah, run around. There you go. Okay, all right, now we can have a seat. I have to lose a couple pounds before the wedding, so we're going to have to do that all the time. That's sad that that's enough to make me lose a couple pounds. Okay, in your Google Classroom, there is a packet of notes called something Trig Notes. You can open up your Trig Notes. We're going to start some trigonometry. Trigonometry. Get the trig, baby. Time for trig. Are you all excited? Trigonometry. I just like saying that. Annalie, it's your birthday?
49 inches.
Ah, lovely.
49.
Okay, how we doing? Everybody got them open? Yes, sir. Yes, but you can't have your iPad while you do it if you charge it. So you can charge it, but you're not going to be able to write on it. And that's okay. Okay. So we're just going to kind of introduce trigonometry today. Normally, in pre-calculus, you already know this stuff. However, I have discovered that in the last couple years, our geometry has been very weak in trigonometry. So, and I hate to make excuses, but we are still feeling the effects of the COVID pandemic school shutdown thing, right? So what's happened, although you guys were you in geometry or algebra 1? Right. So what's happened, because initially when this first happened, as math teachers, we were like, okay, so in pre-cal, I was expecting, like last year, I knew that my pre-cal students were very weak on this because I knew that this was what was covered during the virtual school time, right? And I thought, oh, okay, that's going to be okay after that. But what's happened is because you guys had some skills that you were weak on because you were in Algebra 1, then in geometry, you didn't get through as much as you needed to get through. So it's like, it's just filtering through. And we've discovered that instead of just clearing out in 2 or 3 years, we think it's going to take significantly longer to reverse the effects of having an entire quarter basically being taught to you virtually. And to be honest, I think in math, we're feeling the biggest impact of that going on because of the way math builds on itself. So, whereas normally we would be flying through this very beginning, you need to let me know whether or not I'm going too fast, okay? Because this is just one of those, it's unfortunate. I don't know what else to tell you. It's unfortunate. So we have to make sure that we get it. If you don't get the foundation here, you're not gonna get trigonometry, period. Okay? All right? So everybody's awake? Want to do more calisthenics? I don't know, he does. She wants to do little jumping jacks. Do you guys do jumping jacks still? Caitlin, you look asleep. You look asleep with your eyes open. You're very awake? I can tell. Yeah, okay. Okay, so let's start by talking about some terminology, okay? So one of the places that we use trigonometry a lot, actually trigonometry is used a ton of times. So we saw that logarithms, solving logarithmic equations, we see the use of logarithms. It's funny, I was in Mr. Roberts' classroom this morning, and I can see he's got, in chemistry, he's got some equations up there with log in it, right? How many of you are in chemistry class and you see log? Yep. Is that AP Chem or just? Yeah, he got some log equations in there, right? So there's some application, right? Log equations show up a lot in the scientific world, right? We saw examples of um, seismic activity, right? The Richter scale. We saw Newton's law. We see it just in chemistry in general. So a lot logarithmic equations show up a lot there. Exponential equations show up a lot in the financial world. Okay, compound interest, right? Trigonometry shows up a lot in the scientific world, but more the physical side of it. So, for instance, in projectile motion, right? So, how many of you saw the Eagles game this weekend? Yay, Eagles! Go Eagles! Right? How many of you saw the Eagles game and Devontae Smith with his one-handed catch? Right? How many of you saw that? Did you guys see it? Right? Pretty phenomenal, right? Even though he didn't actually catch it, but that's okay because their stupid coach didn't challenge it. So anyway, he catches the ball, right? So in football, right? If we throw the football, right? And here Devontae Smith leaps up and catches it right there, right? Okay, that's a projectile. Projectiles have both a horizontal and a vertical motion to them. Calculating that horizontal and vertical, what we call components of that projectile, involve trigonometry, right? So when a kicker kicks the ball, right, when he's further out, what do you notice about when he's kicking for a field goal? When he's further out, it's actually the opposite. It's going to be lower because he needs more horizontal distance, right? If the field goal is shorter, he tends to get a higher field goal because he needs more height than distance, right? Same thing. Let's talk about missiles, right? If you're in the Navy, right, and they're firing a missile from a ship, okay? They fire a missile from a ship. That is a projectile, okay? When I was my senior year in college, I almost went into the Air Force, and one of the things that I wanted to do was ballistics because of the math involved in it. And it's a neat thing because you're sitting there and you're calculating that if you're one of these, I don't remember the actual title, but if you're one of the guys or officers that are working with this part of the military, working with firing missiles and things like that, you have to take a lot of math and you have to take a lot of trigonometry. Okay, it's a ton of trigonometry and a ton of math because you have to calculate. You have to be able to calculate what angle, right? This because not only are you firing a missile, well, guess what? The ship's moving. And it may not be moving in the direction that you're firing that missile. Okay? Your ship might be moving this way, right? My target's Jordan. Sorry, Jordan, right? My target's Jordan, right? Okay, I'm lined up. Okay, I can shoot her. But guess what? I'm moving. And I'm like, wait a minute. Okay. So that guy that's figuring that out has to take into account that he's moving. Not only is he moving, guess what? Jordan's moving because the earth is rotating. Right? And that's not a big deal when we're this far away. But modern day military, I don't know what the word is, modern day battles, right? You've got a missile fired. You don't even see the ship, right? They don't even see their target. It's that far away. And when it becomes that far away, now the rotation of the earth does become an issue. So that kid, and I'm saying kid because they're like 19 years old, right? That guy, he's calculating about the rotation of the earth, the movement of the ship, the wind that might be involved, right? All these things. There's a lot of math that goes into that. Okay. They're not just sticking the thing in there and pressing the button, boink. Okay, good shot. Oh, wait, let me readjust it. No, they're not doing that. It's not like you do on your video games, right? Lots and lots of math goes into that. Okay. Any projectile at all is going to involve trigonometry. Okay. And I think to me that's one of the really fun applications of trigonometry. Okay. Another place that we see trigonometry is what we call sinusoidal waves. Where do you see waves like that? In the medical field. Okay. You ever had the unfortunate task of sitting in a hospital room and you watch a loved one on a monitor, right? And what's it doing? It's going, right? Hopefully pretty steady. That's a sinusoidal wave. That's trigonometry. Okay, so there's tons of trigonometry in the real world. Okay, we're going to go outside during this unit and we're going to measure the height of some trees and some towers, and we're going to measure the height of the football goal post, and we're going to use trigonometry to do that. Okay. And granted, I always have students say, "Oh, I'm not going to do that. I'm just going to get my device and click it, and boom, there it is." Well, great. That's good. Okay. I prefer to be the one that's actually programming and making the device and not the one that's just using it. And you guys should be that way too, because you're the cream of the crop. Okay? You're taking honors pre-calculus. And some of you are bored with it because it's so easy for you. You're the cream of the crop. So don't be that person that's just using the technology. You're the people that are making the technology. Somebody's got to know the actual math behind it. You're the people, you're the ones. You're going to make it. You are the Bill Gates of your generation. Okay? You're the cream of the crop. Don't sit there and say, I'm just going to use my calculator. That's for the kid that's struggling to pass Algebra 1. He gets to say, I'm just going to use my calculator. You get to say, I'm going to make a better calculator because I needed to do X, Y, Z. All right? So don't sit back and just, that's all right. There's machines that do that for us because maybe the machine won't work. Okay? I know I've seen films all the time. You see pilots, right? All of a sudden their computers go down. Well, guess what? They can't just say, oh, okay, wait a minute, stop everything. We've got to wait for the computers to come back up because they're in the air. Right? They've got to be able to do the math. Might take longer and it might be pretty stressful, but they've got to be able to do the math. Okay. So, terminal side and initial side. So, a lot of times what we do is we use what we call vectors to represent motion. Okay? So, I told you a projectile has both a horizontal and a vertical motion, right? So, there's my projectile. Okay? Well, when we talk about a projectile, we break it down into vectors. Right? And the vectors are going to represent the motion for us. So when we talk about vectors, we have what we call an initial side and a terminal side. Vectors look like rays, or they are rays. Okay. The initial side, obviously, is the starting position. And the terminal side is the side after we rotate the vector. So what we do is we draw a vector and we say, okay, that's going to move, it's going to rotate a certain number of degrees, and it ends up at its terminal side. So we have a starting position, we rotate it, and it ends up at its terminal position. Okay? The vertex is the end point of the vector. Okay, not the arrow, but the end point. When we rotate a vector from its initial side, we rotate in a counterclockwise direction. So if we start our vector here, right, we rotate counterclockwise. We rotate up. That's how you can remember that, right? When we rotate in a counterclockwise direction, we have positive angles. Okay? We have a positive angle. So if you look at this, this looks to be, approximately 120 degrees. It's a positive angle. If I rotate in a clockwise direction, we get a negative angle. So if I start here and rotate down, I'm going to have a negative angle. Okay, so going in the negative direction, this is negative 240 degrees. They represent the same position. Okay, this is really important, okay? If I have my initial position here, and I rotate negative 240 degrees. So there's negative 90. Okay, I'm going clockwise 90 degrees. I go another 90 degrees. Now I've gone negative 180 degrees. And then I go another negative 60, negative 240. Look where I ended up. I ended up at the same position as I would if I rotated a positive 120 degrees. This is what we call a coterminal angle. Okay, 120 degrees is the same thing as negative 240 degrees. It's called a coterminal angle because I end up at the same terminal position. I end up at the same end position. Okay? It's called a coterminal angle. So let's look down here. Let's draw in a vector that rotates through 220 degrees. Draw theta, right? This is theta. This is a Greek symbol that we typically use to represent angles. It's called theta. Sometimes you'll see alpha, and sometimes you'll see beta. These are the most common Greek letters that are used for angles. Okay, so draw theta equals 220 degrees. So that means we assume we're going to start at the initial position, of the positive x-axis. This is typically where we start, right here on the positive x-axis. Now, I want to rotate 220 degrees, so I'm going to go counterclockwise. Here's 90. Here's 180. How many more degrees do I have to go to get to 220? 180 plus 40, right? So halfway here, that would be 45. So we're just going to estimate it. This looks like it's right about there. Okay. So this angle, All right, we're going to draw it like this so that you can see where I'm starting. This angle here is 220 degrees. Label an angle that is coterminal. Coterminal. Well, if I had started, see if I can get a better, come on, stop. Okay. If I had started here and gone the other direction, right? Here's negative 90. So I start at the same initial position, but I'm going down negative 90 clockwise, right? How much farther would I have to get now to get to this position? Okay, so let's do a little geometry labeling, right? So this is 180, right? So that means this is 40 degrees right here. What's this angle here? 50 degrees. Okay, so if I go negative 90, I have to go another 50. So that is negative 140 degrees. Okay, negative 140 degrees. That is a coterminal angle to 220. Now, do you notice anything about these numbers? What do they add up to? 360. Because one full time around the circle is 360 degrees. Right? So I didn't even have to sit there and figure it out. I know that a coterminal angle to 220, if I just subtract 360 from that, or subtract it from 360, it's 140. So if I go the other direction, 140 degrees, I've got a coterminal angle. Okay. Let me show you another way to represent some coterminal angles. Okay. Okay, so we already rotated 220 degrees. Well, what if I went all the way around? How many degrees is that? 360. And then I come over and I stop here at this terminal position. How many total degrees have I rotated? Right, 360 plus 220 degrees, 580 degrees. Did I end up at the same terminal position? Yes. So this is also a coterminal angle. Okay, that is also a coterminal angle. Questions on the coterminal angles? Can you give me another coterminal angle, but this time it's in negative degrees? So I know I've got negative 140. Thank you, Kim. I know I've got negative 140. Let's figure out if we can do another coterminal. So instead of going positive, I'm going to go all the way around. There's negative 360. And then go another 140, negative 560, negative 600 degrees. So negative 600, is that right? Yeah, 600 degrees is also a coterminal angle. We could keep going and going and going and going and going, right? There are infinitely many coterminal angles, okay? Okay, when we talk about angles, we usually refer to what we call reference angles. When we do the actual trig involved here, okay, I don't want to get ahead of ourselves, but when I do the trig, what we're actually going to do is we're going to create these right triangles. And we're going to calculate our trig from these right triangles. So in order to do that, right, if I look at this right triangle here, it's this little angle right here that I'm going to pay attention to. I'm not going to pay attention to this big angle here. right? It's that little one. It's what we call the reference angle. The reference angle is the angle that the terminal side makes with the x-axis. It's the acute angle that the terminal side makes with the x-axis. Remember, acute is the little one, right? Less than 90 degrees because it's acute, right? Less than 90 degrees. So the acute angle. We're not referring to this angle here. This is an angle that it makes with the x-axis, but that's not acute. It's the acute angle that it makes with the x-axis. That's our reference angle, right? So if we look at this example up here, okay, draw my vector back in there. Okay, here's my vector. Okay, the reference angle is this angle right here, which is, what did we say it was? 40 degrees. So my reference angle is 40 degrees. And what's going to happen is we're going to have this triangle now with a 40-degree angle right there. And then I know that this angle has to be 50 degrees, right? And we'll work with it like that, okay? So if I want the reference angle for 150 degrees, right? Rotating around, here's 90. 150 is going to bring me right there, right? Right, this is, we know if we went all the way to this line, it would be 180 degrees. So what's this angle here? What's the reference angle? 30 degrees. Okay. Okay. See if you can finish B, C, and D while I hand out the review sheet for you. So part B, I've got 315 degrees. So, oops, rotating all the way around, right? 360 would be all the way around. 315 is going to be right about there. So what's the reference angle? It's referring to this angle right here, which is what? 45 degrees. So that reference angle is 45 degrees. Okay, negative 120. So we're going down this way. So there's negative 90, negative 120. So the reference angle is this angle here. What's that going to be? 60 degrees. 60 degrees, right? 120 plus 60 brings me to 180, which would be here. Okay, the last one, 140 degrees. So, right, there's 180. So it's going to be 40 degrees shy of that. So there's my reference angle, and that's going to be 40 degrees. Okay. Okay, no homework tonight because you have a test tomorrow. We're going to stop there. Is this all familiar to you?